Alright, in this video we're going to talk about the uniqueness of first-order differential equations. And I want to start by solving this initial value problem, this IVP here. So you'll notice that this is a separable differential equation. dy dx equals y to the 2/3. And I'm going to go through this pretty quick. You can hit pause if you need to. We're going to separate, and this is going to be y to the negative 2/3 power dy equals dx. We're going to integrate both sides of the equation. That's going to give us 3y to the 1/3 power equals x plus a constant. Going to divide through by 3 because we're going to start solving for y. That's 1/3 x plus, I'll call it 1/3 c. Solve for y by cubing both sides, and you get 1/3 x plus 1/3 c cubed. Now we're going to plug in this initial value, y of 0 equals 0, and we're going to get 0 equals 0 plus 1/3 c, quantity cubed. And you can take a cube root of both sides and multiply both sides by 3 to get c by itself, and you're just going to get c equals 0. So if I may move down just one step here, the solution to this initial value problem is y of x equals, it comes from this line right here, 1/3 x, the quantity cubed, plus 0, the quantity cubed. You can rewrite that as 1 over 27, that's 3 cubed, x cubed. And either one of those answers is fine. And that looks great, it's all well and good. If you plugged in this y into the differential equation, it should work. You can double check your work. The initial value checks out as well. So this looks great. So why are we doing it? The reason is this right here, it's not the only solution to the initial value problem. I'm going to write that down. You could inspect this just by looking at it and come up with a very, very simple solution to this initial value problem. Another solution to this initial value problem is just simply y equals 0. Literally y equals 0. That's just a horizontal line right on the x-axis there. If you plug that into the differential equation, it works. You get 0 equals 0 for the dE, and it satisfies the initial condition. So yeah, that's a solution to the initial value problem. So because we have two solutions, we have y equals 0 is one solution, we have y equals 1/27 x cubed is another solution, we say that the solution to the initial value problem is not unique. Now this may not seem like a big concern to you. Maybe it's not. I mean, most of you are engineers, but I'd like to think of differential equations as representing real things. And if you have a real situation starting at, say, time equals 0, modeled by this differential equation here, and you get two different outcomes, that bothers me a little bit. If you want to think of this purely mathematically, if you got to the end of this problem and you said, okay, I got a solution, now I'm done, well, technically, you weren't finished. There are times when there's more than one solution to an initial value problem. So technically, this is not a complete answer. So a question we should be asking, maybe more as mathematicians than as engineers, is when do we know, when are we guaranteed that an initial value problem just has one solution? Say we get to the end of the problem and we find a solution, when are we guaranteed that that's it? Let me write down the question. So the question is, when are we guaranteed a unique solution to an initial value problem? The answer is given to us in a theorem. So the theorem takes a little bit of setup. We're given an initial value problem. This is the initial value problem. That's the form that we wanted in. And if you compare this to what we were given earlier, it's pretty close. We have y prime equals some function of x and y. If you look at the problem that we had earlier, we have y prime equals, and that is a function of x and y. There doesn't happen to be an x in there, but that's okay. We have an initial condition, y of something equals something. And in our problem, we had y of 0 equals 0. Okay, so that's the form that we have the differential equation in. All right, let's cut to the chase. This is the theorem right here. We're given an initial value problem. We're guaranteed a unique solution to the initial value problem. That means the only solution, one solution, if f of xy, that function, and its partial derivative with respect to y are both continuous and a box around our initial point. I realize this is pretty funny looking, so let's break it down a little bit. Basically what we have is some differential equation, and we're given an initial condition for this differential equation, and that point goes through the point x naught, y naught, right there. And whatever the solution to this differential equation is, solution or solutions I suppose, it'll go through that point there. It'll pass right through that point. I don't know what it looks like, but we'll say it looks something like that. Okay, that's what the solution looks like. I'm going to get rid of it. What this theorem says is that if this function here, not the solution to the differential equation, but this function in the differential equation is continuous, and its partial derivative with respect to y is continuous in some box around this initial condition, then we're guaranteed a unique solution, at least inside that box. Now, I'm sure this requires an example to clarify, so let's look at the original problem. We had dy dx equals y to the 2/3, and the initial condition is y of 0 equals 0. So we're going to check this initial value problem for uniqueness using the theorem that we just wrote down, and hopefully that'll clarify a little bit what this theorem means. First of all, what is f of xy in this theorem for our problem right here? Well, it's just y to the 2/3 power. What is the partial derivative of that with respect to y? Because we need to look at that as well. The partial derivative with respect to y is just 2/3 y to the negative 1/3 power. So what we're looking for is we're looking to see, is this first function continuous? Yeah, it actually is continuous. It's a funny looking function, but there are no points of discontinuity in that function. How about this function? Is that continuous? Because of the fact that this is a negative power here, we can actually think of this as 2/3 1 over y to the 1/3. So there's a denominator that we've introduced. We know that anytime there's a denominator, we could potentially have a discontinuity, and we do. This is not continuous at y equals 0. So if we were to say draw an xy plane, we could put our initial conditions down in this xy plane. That's our initial condition is just 0, 0. And we could put in this plane everywhere where we have a discontinuity in either f or df dy. So since this is the x-axis and this is the y-axis, y equals 0 is a discontinuity right through the x-axis there. Now you'll notice it's impossible to draw a box around our initial condition that contains no discontinuities. Remember, the theorem says we're guaranteed a unique solution if f of x, y, and df dy are both continuous in a box around the initial condition. There's our initial condition. We could draw any size box around it. We have discontinuities inside of this box. Therefore, we are not guaranteed a unique solution to this initial value problem. Let me write that down. Okay, we have a discontinuity in df dy right here through the point 0, 0, our initial condition, so we're not guaranteed a unique solution to the initial value problem. That is why it was possible way back at the beginning for us to come up with two solutions to the same initial value problem, because we were not guaranteed a unique solution by this theorem that we wrote down here. So a lot of times when I'm doing this in an actual classroom, the next question people ask is, well, couldn't we just move this initial condition? Couldn't we have just moved this initial condition point to somewhere where there wasn't a discontinuity? And the answer is yes. If we were instead given the initial value problem, y prime equals y to the 2/3 power, y of 0 equals 2, notice the only difference here is that this number here is not a 0 anymore, it's a 2. But if we were given this initial value problem, we would actually be guaranteed a unique solution. We could draw our little xy plane. Our initial condition would be right here at 0, 2. Our discontinuities would still be in the same place, but we could draw a box around that initial condition that contains no discontinuities. In fact, we could go even further and say the largest rectangle where we're guaranteed a unique solution to this initial value problem is this top half of the plane. And the way that we would write that is we're guaranteed a unique solution on the set of x and y values such that y is greater than 0. That's it. Now, I know that theorems are confusing and frustrating. I remember it well. But this video is getting too long, so I have to give you a quiz. Here it is. Find the largest rectangle on which we're guaranteed a unique solution to that differential equation. Now, I'll just tell you that the steps are always the same. We always make sure we have the differential equation in the right form. Then we go through and we find discontinuities in our function f of x and our partial derivative with respect to y of that function. We draw a picture with our initial condition and all of our discontinuities, and we draw the largest box we possibly can that contains no discontinuities around our initial condition. So follow that process, and this should work out pretty well for you. Good luck, and I'll see you in class.